Good evening, sir.
Yes, good evening. Am I audible?
Yes, sir.
So last day we were discussing about Hamilton's equation of motion, which are Q dot equal to del H del P and P dot equal to minus del H del Q. Here H is the Hamiltonian, which is function of Q and P, and here Q and P are generalized coordinates and generalized moment respectively. Okay. So H is a function of Q and P. Now I will define Poisson's bracket. Now what is this? Let's say there are two functions f and g. Then the Poisson's bracket of these two quantities f and g will be this: del f del q del g del p minus del f del p into del g del q. Okay, so this is called the Poisson's bracket of two functions f and g. Now what will be the Poisson's bracket for this quantity q and p? So this will be equal to del q del q del p minus del q del p into del p del q. Okay, here q and p are independent of each other. Okay, q and p are two independent variables. So del q del p will be equal to 0, and del p del q will also be equal to 0. So this thing is 0. Now what is this? This will be of course equal to 1. So the Poisson's bracket of generalized coordinate and corresponding canonically conjugate momentum is equal to 1. Okay, this is clear.
Yes, sir.
Now I will talk about canonical transformation. So what is this transformation? This is the transformation of generalized coordinate and momentum to another coordinates. Okay, let's see what's that. So we have already q and p. This is generalized coordinate and generalized momentum. Okay, so we are transforming it to capital Q comma capital P. So this we will call canonical transformation only if q dot capital Q dot is equal to del k del p and p dot equal to minus del k del q. Now what is k? K is the new Hamiltonian, which is a function of capital Q and capital P. If this condition is satisfied, then we'll call this transformation to be canonical. Okay. So here also capital Q and capital P are two canonically conjugate quantities, right? This capital Q is the generalized coordinate and capital P is the corresponding canonically conjugate momentum. Okay, so what will be the Poisson's bracket of these two quantities? This will be again equal to 1. Now if you write this Poisson's bracket as a in terms of small q and small p, then it will look like this: capital Q del q del capital Q del small q into del capital P del small p minus del capital Q del small p into del capital P del small q. Okay, so this will be equal to 1 if this transformation from small q small p to capital Q capital P is canonical transformation. Okay, so this is canonical transformation only if the Poisson's bracket of the new two canonically conjugate quantities is equal to 1. Okay, so there is one message from this calculation, that is the Poisson's bracket remains invariant under canonical transformation. Okay, okay, this is clear.
Yes, sir.
Okay, now we'll solve a problem. Okay, Hello everyone. In this video, I shall discuss the solution of question number 23 of GATE Physics 2020. This is a numerical answer type question. Let small p be the momentum conjugate to the generalized coordinate small q. If the transformation capital Q equal to root 2 into small q to the power m into cos small p and capital P equal to root 2 into small q to the power m into sin small p is canonical, then we need to find out the value of m. Let's solve this question. The Poisson's bracket of small q and small p is equal to 1. If the transformations given by these two equations is canonical, then the Poisson's bracket of capital Q and capital P will also be equal to 1. Now capital Q is equal to root 2 into small q to the power m into cos small p. So the partial differentiation of capital Q with respect to small q is equal to root 2 into m into small q to the power m minus 1 into cos small p, and the partial differentiation of capital Q with respect to small p is equal to minus root 2 into small q to the power m into sin small p. Capital P is equal to root 2 into small q to the power m into sin small p. So the partial differentiation of capital P with respect to small q is equal to root 2 into m into small q to the power m minus 1 into sin small p, and the partial differentiation of capital P with respect to small p is equal to root 2 into small q to the power m into cos small p. In this equation, we put the values of these quantities. After some simplification, we obtain that 2m into small q to the power 2m minus 1 into cos square small p plus 2m into small q to the power 2m minus 1 into sin square small p is equal to 1. Now cos square small p plus sin square small p is equal to 1. So we have 2m into q to the power 2m minus 1 is equal to 1. Now 1 can be written as q to the power 0. Now equating the exponent of q on both sides, we get 2m minus 1 equal to 0. This means 2m is equal to 1, or m is equal to half, or 0.5. So m is equal to 0.5. So in this question, the correct answer is 0.5. So the value of m is 0.5. Any question from this?
No, sir.
So this is clear. Just I have explained. You have to just find out the partial differentiations of capital Q and capital P with respect to small q and small p respectively. Okay, and put the values. So this we have already discussed. Now let's see. There are three coordinates x, y, and z. Okay, x, y, z, and three components of the momentum. So this is basically a three-dimensional system. Okay, for one particle, okay, single particle, three-dimensional system. So what will be the commutator of these two?
0.
Right. So what will be the formula for this? This will be, let's say, these are F and G. So there are three coordinates and three components of the momentum. So you have to take sum over I, where I runs from 1 to 3. So what are xi's? Xi is equal to x, y, and z for I equal to 1, 2, and 3 respectively. Okay, and pi is equal to px or py or pz if I is equal to 1 or 2 or 3. Is this clear?
Yes, sir.
Okay. So if you use this formula and if you find out xi, xj Poisson bracket, then it will be equal to delta ij. Now what is this delta ij? Delta ij is equal to 1 if I is equal to j, and if I is not equal to j, then it will be equal to 0. So this is equal to 1 if I is equal to j, and 0 if I is not equal to j. Similarly, sorry, this should be
PXI.
right,
PI.
pj. And if you calculate this, then it will always be 0, okay, for all values of I and j. Similarly, if you calculate this, then it will again be 0 for all values of I and j. Okay, so then based on this we will solve a problem now.
Hello everyone. In this video, I shall discuss the solution of question number 25 of GATE Physics 2021. This is a numerical answer type question. If A and B are constant vectors, small r and small p are generalized positions and conjugate momenta respectively, then for the transformation capital Q equal to A dot small p and capital P equal to B dot small r to be canonical, we need to find out the value of A dot B. Let's solve this question. If the transformations mentioned in this question is canonical, then the Poisson's bracket of capital Q and capital P will be 1. This means sum over I del capital Q del Ri into del capital P del Pi minus del capital Q del Pi into del capital P del Ri is equal to 1. Now capital Q is equal to A dot small p. This capital Q can also be written as sum over j Aj into small pj. So del capital Q del Ri is equal to 0. Del capital Q del small pi is equal to sum over j Aj delta ij. This can be simplified to Ai. So del capital Q del small pi is equal to Ai. Now capital P is equal to B dot R. So capital P can also be written as sum over j Bj into Rj. So del capital P del Ri is equal to sum over j Bj into delta Ij. This can be simplified to Bi del capital P del small pi is equal to 0. Putting the values of the partial differentiations in this expression, we obtain sum over I Ai into Bi is equal to minus 1. Now sum over I Ai into Bi can also be written as A dot B. So A dot B is equal to minus 1. So the value of A dot B is equal to minus 1. So in this question, the correct answer is minus 1.
Okay. So in this problem, we have to again find out the Poisson's bracket of this capital Q and capital P. But there are this R and P vectors have multiple components. Okay, how many components are there? That's not important. Okay, there are multiple components. So if the transformation is canonical, then again the Poisson's bracket of capital Q and capital P will be equal to 1. Now you have to use this formula that I have just mentioned a few minutes ago. So capital Q is equal to A dot P. So this you can write as sum over j Aj into Pj. So this is like you have A dot B. So how you write that? So you write the x component of A vector times the x component of P vector plus the y component of y component of A vector and multiplied with the y component of b vector plus the z component of a vector into the z component of b vector. So let me write it here.
That's clear. Ax bx plus ay by plus az bz.
So you all know about it, right?
Yeah.
So this is clear, right? So what will be del capital Q del Ri in this case? It will be equal to 0 because there is no Ri dependence here, and this Pi and Ri are independent coordinates, independent variables. Okay, so this will be equal to 0. And what will be del capital Q del Pi? This will be equal to sum over j. Aj is a constant, okay, as a and b are constant vectors, and then you have del pj del pi. Okay, so this will be equal to 1 only if I is equal to j, otherwise it will be equal to 0. So this is equal to delta ij. Is this clear?
Yes, sir.
Now you have to use this summation. So this, when j is not equal to I, for all values of j which is not equal to I, this is equal to 0. This delta ij
0.
is equal to 0. Yes, any question?
No, sir. I'm saying
Okay,
it will be 0.
right. Okay, so for only for j equal to I, this is equal to 1, and only that term of this summation contributes. Okay, I mean non-zero. So for j equal to I, only this term contributes. So for j equal to I, of course it will be equal to ai. So the value of del q del pi is equal to ai. Similarly, capital P is equal to b dot r. So this you can again write it as sum over j bj into rj. Again you perform this same thing. So bj is constant, so this is here, and delta, I mean del rj del ri is equal to again delta ij, which is equal to 1 if I is equal to j, otherwise it will be equal to 0. So again this j equal to I term contributes. So this is equal to bi, and del capital P del small pi is equal to 0 because there is no small p dependence here, and this r and small p are independent variables. So this is equal to 0. Now you put in this expression. So this term is 0, this term is again 0, and this term is ai, and this term is bi. This we have already found here, and here. So we have sum over I ai into bi equal to -1, and as I have mentioned before, this you can write it as a dot b. So a dot b is equal to -1 in this problem. So a dot b is equal to -1. That's the answer. Okay, any question?
No, sir.
Okay, now we'll solve now we'll solve another problem.
Hello everyone, in this video I shall discuss the solution of question number 43 of GATE Physics 2018. This is a numerical answer type question. For the transformation capital Q equal to root 2 into root small q into e to the power minus 1 plus 2 alpha into cos small p and capital P equal to root 2 into root small q into e to the power minus alpha minus 1 into sine small p to be canonical. We need to find out the value of alpha. Here alpha is a constant. Let's solve this question. The Poisson's bracket of small q and small p is equal to 1. Now, if the transformation given by these two equations is canonical, then the Poisson's bracket between capital Q and capital P will also be equal to 1. Then we have this equation. Here capital Q is equal to root 2 into root small q into e to the power minus 1 plus 2 alpha into cos small p. So the partial differentiation of capital Q with respect to small q is equal to root 2 into half into q to the power minus half into e to the power minus 1 plus 2 alpha into cos small p, and the partial differentiation of capital Q with respect to small p is equal to minus root 2 into small q to the power half into e to the power minus 1 plus 2 alpha into sine small p. Capital P is equal to root 2 into root small q into e to the power minus alpha minus 1 into sine small p. So the partial differentiation of capital P with respect to small q is equal to root 2 into half into small q to the power minus half into e to the power minus alpha minus 1 into sine small p. The partial differentiation of capital P with respect to small p is equal to root 2 into small q to the power half into e to the power minus alpha minus 1 into cos small p. Now, if the transformation mentioned in this question is canonical, then the Poisson's bracket of capital Q and capital P is equal to 1. Putting the values of the partial differentiations in this expression, and after doing some simplification, we get e to the power alpha minus 2 into cos square small p plus e to the power alpha minus 2 into sine square small p is equal to 1. Now cos square small p plus sine square small p is equal to 1. So we have e to the power alpha minus 2 equal to 1. Now 1 can be written as e to the power 0. From this equation we get alpha minus 2 equal to 0, or alpha equal to 2. So the correct value of alpha is 2. So the value of alpha is 2.
Is there any question?
No, sir, it's clear.
Now let's continue our discussion. and after that we will solve another problem. Okay, so here we are talking about this q dot equal to del k del capital P and P dot equal to minus del k del capital Q, and k is the Hamiltonian, which is function of capital Q and capital P. So last day I have shown you that L prime equal to L plus df dt, where f is a function of generalized coordinate and time. Here L prime and L both satisfy Euler-Lagrange equation. So any one of them can be considered as a Lagrangian. Okay. So these two Lagrangians differ by the total time derivative of a function, which is a function of generalized coordinate and time. Now you write this k equal to capital P into q dot minus L prime. Okay, and h equal to p q dot small p small q dot minus L. Then what will happen? Write in this expression, then you will get this, right? If you put them in this expression. Okay. Now let's say,
So what is Q here?
sorry,
K. What is K?
I'm explaining that. K, let's say k is another Hamiltonian, okay, which is a function of capital P and capital Q. Okay,
Then Raj coordinate.
so then if you take capital K equal to H, so what is this approximation here? Not approximation, we are considering only that the Hamiltonian is same. Okay, then what will
Yes, sir.
happen? P into dq dt, I mean this q dot is equal to dq dt, right? And this small q is equal to this you can write then, and if you multiply both sides with dt, then you have this. So if you have any canonical transformation from small p small q to capital P capital Q, then it will satisfy this equation. Now what does this mean? So you have to just find out del dq as a function of small p and small q. Okay, and this capital P is already given to you as a function of small p and small q, right? So you have to just find out these things, and this difference will be equal to the change, I mean d of some function f. So total change, I mean total derivative of some function f. So I think we'll take one example, then it will be very clear to you. So what example can I use here? If this equation is satisfied, then the transformation will be canonical, right? So in the problem we just solved, there was so what is the final value of alpha? This is equal to 2. So for alpha equal to 2, this was canonical, right? So let's consider this problem and take alpha equal to 2. So if you take alpha equal to 2,
to the power 3.
right, because
E to the power minus 3.
so what will be dq in this case? Okay, dq is equal to e to the power 3 into root 2 into half into q to the power minus half into dq into cos p minus q to the power half into sin p dp. So this you have to find out. So this e to the power 3 into e to the power minus 3, this is equal to 1. So this root 2 is equal to 2. Now here we have root 2 q to the power half into here we have q to the power minus half. So this is equal to 1. So this is the quantity.
minus p dq in minus
So there should be only one. Is any problem? Oh, there is a minus. No, sorry.
minus p dq.
Hmm. I think it's too complicated. Okay, so if anyone can do it. So we could take an easy problem also. But anyway, it can be written in terms of d of some f. Okay, so if it is a canonical transformation. Okay, any guess? Can we? How can we do that? Anyone? I think no. Okay, so as there is some problem, so we'll discuss this problem. This p dq minus small p dq equal to df with an example on the next class. But today we'll solve a problem based on Poisson distribution. Okay, I think the verification of canonical transformation through the Poisson's distribution, Poisson's bracket is easier than this, right? Yes or no?
Yeah, it is.
That
It is
was the
difficult.
easier method, right? Because you see,
Yeah,
this
previously.
here we are checking whether this is a canonical distribution or not, but uh, it seems uh, actually we can write it in this form because this is of course canonical transformation, but uh, there is no way to actually find out this thing. For some problem it is easier to write in this way. Okay, so now we'll solve a problem on Poisson's bracket actually.
Hello everyone. In this video, I shall discuss the solution of question number 54 of GATE Physics 2022. This is a multiple select question. A system with time independent Hamiltonian H has two constants of motion F and G. Here F and G are functions of Q and P. Then we need to find out which of the following Poisson's brackets are always zero. Let's solve this question. In this question, F is a constant of motion. So df dt is equal to 0. Now df dt can be written as del f del q into q dot plus del f del p into p dot. From the Hamiltonian's equation, q dot can be written as del h del p. Similarly, p dot can be written as minus del h del q. So we have del f del q into del h del p minus del f del p into del h del q equal to 0. So the Poisson's bracket of f with h is equal to 0. Similarly, g is a constant of motion. This means the Poisson's bracket of g with h is equal to 0. Now we'll calculate the Poisson's bracket of h with a plus g. This can be written as the Poisson's bracket of h with f plus the Poisson's bracket of h with g. The Poisson's bracket of h with f is equal to 0. And also the Poisson's bracket of h with g is equal to 0. This means the Poisson's bracket of h with a plus g is equal to 0. This means option A is correct. There is an identity of the Poisson's bracket which is called Jacobi identity. The Jacobi identity is given by this equation. Here the Poisson's bracket of G with the Hamiltonian H is equal to 0. So the first term of this Jacobi identity is equal to 0. Similarly, the Poisson's bracket of H with F is equal to 0. This means the second term of this Jacobi identity is equal to 0. This implies that the third term of this identity is also equal to 0. This means the Poisson's bracket of the Hamiltonian with the Poisson's bracket of f and g is equal to 0. So option B is correct. Now we'll calculate the Poisson's bracket of h plus f with g. This can be written as the Poisson's bracket of h with g plus the Poisson's bracket of f with g. Here the first term is 0 because the Poisson's bracket of h with g is equal to 0. But the second term is non-zero in general. So the Poisson's bracket of h plus f with g is non-zero in general. This means option C is not correct. Now we'll calculate the Poisson's bracket of H with H plus Fg. This can be written as the Poisson's bracket of H with H plus the Poisson's bracket of H with Fg. The Poisson's bracket of H with H is equal to 0, and the Poisson's bracket of H with Fg can be written as the Poisson's bracket of H with F into G plus F into the Poisson's bracket of H with G. Here the Poisson's bracket of H with F is equal to 0. Also the Poisson's bracket of H with G is equal to 0. So all the terms of this expression are 0. This means the Poisson's bracket of H with H plus Fg is equal to 0. So option D is correct. So we have found that option A, option B and option D are correct. So in this question, option A, option B and option D are correct.
That's clear.
So this is clear, but
Yeah.
something to say here. So let's say you are given a quantity, okay? So you have to check whether this quantity is a constant of motion or not. Then how will you check? Let's say the quantity is independent of time. There is no explicit time dependence of the quantity. Okay, then you have uh, actually if this quantity is constant, then you have df dt equal to 0. So this df dt can be written as del f del t plus these terms. Okay, so del f del t will be equal to 0 if there's no explicit time dependence of this quantity. Okay, so this term is 0 because there is no time dependence. Now this del f del q into q dot plus del f del p into p dot is equal to 0. Now you are using q dot equal to del h del p and p dot equal to minus del h del q. Okay. Now this is equal to the Poisson's bracket of f with h, the Hamiltonian, right? So this is equal to 0. So let's say there is some unknown quantity which is given to you, then how will you check whether this is a conjugate quantity or not? Then you have to just find out the Poisson's bracket of this quantity with the Hamiltonian of the system. If the quantity is independent of explicitly independent of time and the Hamiltonian is also explicitly independent of time, and if this is equal to 0, then the quantity is a conjugate quantity. Okay, so here this is a conjugate quantity, so this is equal to 0, this Poisson's bracket again, and for g this is equal to 0. So this is just simple thing. So option A, there is nothing to say. There is one thing to say in option B. There is some identity which involves the Poisson's bracket of three quantities or three functions, f, g and h. Okay, so this is the identity, and here for this problem this term is 0 because g is a constant of motion, and f this term is 0 because f is a constant of motion, and this term is also 0 because of this Jacobi identity. Okay. So here I have nothing to say because this is non-zero, because it may be 0, may not be 0, we don't know. For some function f and g, it may be equal to 0. For some other function it may not be equal to 0. So this we cannot say that this will always be equal to 0. So this option is not correct. Here just the thing, the Hamiltonian and the Poisson's bracket of Hamiltonian with itself is equal to 0. Okay, so there is one physical significance of this thing. If the Hamiltonian does not depend explicitly on time and then the Hamiltonian is a conserved quantity. This is actually equal to energy, right? Total energy of the system from this equation. If del H del T is equal to 0 and F is equal to H, so this is H Poisson's bracket, which is equal to 0. So H is a conserved quantity, and in this case the Hamiltonian is equal to the total energy of the system. And here we have used the here in this case the Poisson's bracket of Hamiltonian with product of two functions. We have to just use the partial differentiation of two functions, then you will get this expression from this. Okay, this Poisson's bracket of H and F multiplied with G into F into the Poisson's bracket of H and G. Okay, and these two are equal to 0 because F and G are constants of motion, so this is equal to 0. So any question?
No, sir.
If not, then we'll stop here today. We'll continue our discussion on Poisson's bracket, canonical transformation, and other things like related topics like action angle variables, and also calculate action, the integral L dt, right, which is Hamilton's action, for one problem on the next class. And if we have time on the next class, then we'll also show you this p dq minus small p dq equal to df for one canonical transformation example. Okay, simple example. So okay, so let's stop here today. We have our next discussion on which day? I think it's 29th, right? 29th from 6 p.m. Okay. Thanks everyone.
Thank you, sir.
Thank you.
Good night.
Thank you, sir.